Hello, it's Miss Collins here. We're going to start Advanced Higher Chemistry with the Inorganic Chemistry unit. Normally we would start doing all the practical work, but because of the current situation that's not possible. This first Inorganic Chemistry unit covers some aspects which will be useful if you've got higher physics, but don't worry if you don't have any physics, because we're going to go through everything step by step. We're going to start with electromagnetic radiation and atomic spectra. There will be a video talking you through the notes. You have your own copy of the notes and you can highlight your own copy. At each point during the notes, there'll be questions for you to answer. You can either take a photo of your work if it's handwritten, or you can type your responses to the questions and submit them. There's also a short multiple choice check test for each section as well. So we'll start with electromagnetic radiation. Now, electromagnetic radiation can be described as a wave, which means it has a wavelength and a frequency, and it can also be described as a particle. And this is why we say that it has a dual nature, because it can be described as sometimes as a wave, sometimes as a particle. There are key terms about waves that you need to know. Physicists, you probably should be aware of these already. The wavelength is defined as the horizontal distance from one point on a wave to the same point on the next wave. And it's measured in meters. Most of the time in chemistry we'll be referring to radiation in the visible part of the electromagnetic spectrum, and we don't tend to use the units of meters, we tend to use the units of nanometers. Now 1 nanometer is 1 times 10 to the minus 9 meters. So that means to convert from nanometers into meters, you would multiply by 10 to the minus 9, and to convert meters back into nanometers, you would multiply by 1 times 10 to the 9. You also need to know the key term of frequency. Frequency is the number of waves that pass a point in 1 second. And it's measured in seconds to the minus 1, which is usually given the name Hertz, HZ for the symbol. The velocity is the other key term you need to know about waves, and the velocity of electromagnetic radiation is constant. It is in fact the speed of light, so it has a value of approximately 3 times 10 to the 8 meters per second. You can find the value of all the constants that you need for advanced higher chemistry on page 22 of your data booklet. The equation to link velocity, frequency, and wavelength is C equals F lambda. Lambda is the Greek symbol for wavelength. This can obviously be arranged to give you F equals C over lambda, or lambda equals C over F. The different types of radiation are arranged in order of wavelength, and this is known as the electromagnetic spectrum. For advanced higher chemistry, you need to know the key points, so the key types of radiation found in the EM spectrum. So we've got gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio. Gamma rays and X-rays, at this top end of the spectrum, they have a short wavelength and a high frequency. At the radio wave end of the spectrum, they have a long wavelength and a low frequency. You need to know the whether the relationship between wavelength and frequency for different waves. Okay, if we have a look at photons. So when electromagnetic radiation is absorbed or emitted by a matter, sometimes it can behave more like particles than like a wave. And these particles are known as photons. A photon carries quantized energy proportional to the frequency of radiation. This word quantized means that it has a specific value. It's like a packet of energy. If a photon is absorbed or emitted, then energy is gained or lost by the electrons within that substance. If you have photons in high frequency radiation, they can transfer greater amounts of energy than photons in low frequency radiation. Okay, so the energy is directly proportional to the frequency. We can represent that using this equation here. This one won't highlight for me because it's written as an equation, okay? You can highlight that yourselves. This equation here, E equals HF, will give you your energy value in joules. We can substitute in F for our previous equation, so we can have H times C divided by lambda. This constant H is Planck's constant, and it has a value of 6.63 times 10 to the minus 4 joules seconds. Again, that's on page 22 of your data booklet, so it's not one you have to remember. Now, because we're chemists, we like to work in moles rather than single photons. So to calculate the energy in joules per mole, we can do E equals L times H times F. Now this L represents Avogadro's constant, and it has a value of 6.02 times 10 to the 23, again on page 22 of your booklet. And it's the number of formula units in 1 mole of a substance. So it could be the number of atoms in 1 mole of a metal. It could be the number of molecules in 1 mole of water. Okay, but this is the only place that you will use this in advanced higher chemistry. Again, you can substitute in for C over lambda for F, and to get the equation E equals LHC divided by lambda. This obviously gave you in joules per mole. As chemists, we like the units of kilojoules per mole. So to calculate the energy in kilojoules per mole, we just divide by 1,000. This equation was in joules. To convert it to kilojoules, divide by 1,000. This is probably the most useful equation that you'll use, not in chemistry questions in advanced higher. The information about the waves is not normally given as frequency, it's normally given as wavelength, so probably you'll find the second part of this equation much easier to use. Only thing you need to remember is this wavelength bit here, okay, must be in meters. So if you're given the wavelength in nanometers, you have to convert it into meters in order to carry out the calculation, otherwise you'll get an incorrect answer. You will not get the answer in kilojoules per mole. You can rearrange this equation as well to make lambda, wavelength, the subject, and that would be lambda equals LHC divided by 1000 E. That will give you your answer in meters. To convert it into nanometers, you must multiply it by 10 to the power of 9. You should now be able to answer questions 1 to 5 in your inorganic chemistry questions document. And there should also be a check test that you can complete as well. Thank you very much. If you have any questions,